Hello everyone, nice to meet you again. This is Dr. Bajigni. This is lecture number 9. In this video, I will cover chapter 7, method of analysis. As I explained earlier, the meaning of analysis of a circuit is to find the voltage across the elements, such as resistors, to find the current through the elements, through the resistors, and find the power either consumed by the elements or produced or delivered by the elements, such as a voltage. So with Ohm's law and Kirchhoff's law established, they may now be applied to circuit analysis. Now, in the previous chapters, we only analyze a circuit with one loop. So if we do if we draw just a circuit, one voltage source, few resistors in series, R1, R2, R3, and the volts. So it's easy to find I. So if we, either apply KVL, we say minus V, and then plus I R1, plus I R2, plus I R3 equal to 0. And then we can solve for I. So I will be V over R1 plus R2 plus R3. And we name this total of the resistance to be equivalent to R, equivalent to RT. So I would be equal to V over R equivalent or IT. And then we go back to the circuit and we determine the voltages across each element, such as V1 across the resistance R1, and then V2, the voltage across the R2. This will be V2 minus V2, and this will be V3. So we can say V1 is equal I times R1, and then V2 is equal I times R2, and V3 equal to I times R3. And then we can also apply or use the power formula. P is equal I times V, or I square R, or V square over R. So if we want to find P1, the power produced or dissipated by the resistance R1, so it will be, we could use I times V1, or I square times R1, or V1 square over R1, and so on for P2 and P3. Now, what happens if we have a circuit that has more than one source or more than one, for example, loop? So this is V1, V2, and this is R1, R2, this is V2, and this is R3. So now using KVL, just one KVN applied on this circuit is very hard, and also using Ohm's law by itself is very hard. So that's why we will introduce a new technique or two type of techniques to analyze the circuit. One of them is the nodal analysis, and the other one is the mesh analysis. Now, nodal analysis, which is based on Kirchhoff's current law, and the mesh analysis, which is based on Kirchhoff's voltage law. Any linear circuit can be analyzed using these two techniques. The analysis will result in a set of simultaneous equations which may be solved by Cramer's rule or computationally using MATLAB, for example. This is if we want to use the computer analysis, we can use the MATLAB or any other computer program. Also, there's other two techniques to solve those equations. They call the elimination method and the substitution method, and we will talk about this later on. Okay, mesh analysis. Now, let's give the definition of a mesh and what is the difference between a loop and a mesh. If we have this example, let's say we have a voltage source, we have a resistance here, another resistance here, another resistor here, another voltage source here. Now, how many loops here and how many meshes? So as we defined, a loop is a closed path with no node passing more than once. So for example, we could say that this is a loop, say loop 1. This is a loop because it's a complete path, loop 2. This is also a loop. Okay, start from here, go around. So this is a third loop or loop 3. So now we have 3 loops, but we have only 2 meshes. So again, I'm going to redraw the circuit one more time. So it's a loop and a mesh. This is also a loop and also called a mesh. Okay, so again, as you see here, the loop or the mesh is the path that goes in parallel with the elements here. See here, it doesn't intersect this line here. While the loop could intersect an element such as this one. So we could see here, here's a mesh. Here is a mesh and a loop. So every mesh is a loop, but not every loop is a mesh. So again, how many meshes we have? We only 2 meshes. Yeah? We have 3 loops, but 2 meshes. So this is the difference between a loop and a mesh. Okay, so what are the steps of using mesh analysis? Mesh analysis follow these steps. Step number 1, assign mesh currents I1, I2, IN to the N meshes. So again, we only assign currents around meshes, not loops. Then second step, apply KVL to each of the N mesh currents, and then solve the resulting N simultaneous equations to get the mesh currents. So these are 3 steps to follow. If we follow these 3 steps, it will be very easy to find the solution and to analyze the circuit, which means to find all the currents flowing in those elements, to find all the voltages across those elements, and to find the power consumed or delivered by these elements. So let me just draw an example here. Let's say I have a circuit like this, same as the previous one. Here's an R1, here's an R2, here's an R3. So the first thing I need to do, first step is to assign mesh current. So this is I1 and this is I2. So if you have 3 meshes, then you assign a current number 3, I3. If I have 4, assign 4. That's the first step. And then we need to apply KVL around each loop. So that's one, let's say this is V1, this is V2. So to do that, I could say just apply KVL around loop number 1. So it would be minus V1 plus R1 I1 plus R2, R3, I1. But here, if we look down here across the R3, actually there's two currents flowing through the R3. So that means there's two voltage drops, one created or caused by I1, which is R3 times I1, and then the second voltage drop across the R3 is caused by the neighboring loop or mesh, which is I2. But since I2 is in the opposite direction of I1, so the voltage drop will be a minus. So it will be minus I2 times R3 equal to 0. So this is equation number one. Would be, so applying KVL will determine or will give me an N mesh equation. So it depends on how many meshes I have. I should have 3 or 4 or 5, depends on the number of the meshes. I should have a number of the equations or number of simultaneous equations to solve. Now, if we apply KVL, so apply KVL around loop 2, around mesh again, we call this is a loop and also in the same time as a mesh. So again, this is also a mesh, this is also a loop, but we don't use this loop to solve for the mesh analysis. We only use the meshes to solve for the voltage, or we analyze the circuit. Okay, so now if I go back to apply KVL around mesh number 2, what I have I2 times R2, and then I have I2 times R3, and also I have the voltage V2. Now V2 will be a plus because I2 is hitting the sign, the plus sign of the V2. So it will be V2 equals to 0. Now I should organize. Now again, I should also find the voltage contributing by the resistance RT. So I should have also minus I2 times R3. Why is minus? Because, I1 minus I3 equals to 0. So let me fix this here. So again, I have a voltage drop created by, let me redraw the circuit here. So I have voltage drop created by R2 because of I2 and R2, and then I have voltage drop caused by R3. Always is a plus, okay, because current always go from, since I assume the current going in this direction, clockwise, for both I1 and I2. So that means this is a plus minus, and this is a plus minus. So the voltage drop across R2 and R3 caused by I2, it has a plus sign, plus and a plus. Now, the contribution of I1 toward the R3, it's a minus because I1 is in the opposite direction of I2, so it would be minus I1 times R3. Okay. Okay, so let's look to this example here, what we see here. So the above circuit has two paths that are meshes. So this is a mesh, which is A, B, E, and F. And then I have another mesh, a second mesh, will be B, C, D, E. Okay, these are the two meshes here. Now I need to apply KVL to those two meshes. So again, let's start with mesh number 1 or loop number 1. This is 1 and this is 2, mesh 2. So to apply, so I start with a V1, so it will be a minus V1. and then I1 multiplied by R1. So again, the voltage drop has to be a plus, because since I assume the current going clockwise for I1, that means this has to be a plus, this has to be minus, and the same thing for the R3. Okay, so now I'm looking for loop number one. Now I'm looking for loop number one because I am having I1 passing through the mesh number one. So I will focus on I1. So I1 will be multiplied by R1 plus I1 multiplied by R3. Okay, and then and then we have the minus sign. Now, again, there's two ways when you come for the resistor or the element that it has been shared by two meshes. So we see R3 was shared, or the common between loop 1 and loop 2. We see that R3, it is a joint between two loops. So we can use, as the book says here, it will be R3 multiplied by I1 minus I2. Why minus I2? Because I2 is in the opposite direction of I1. So I1 moving down and I2 moving up. So that means they are in opposite direction then. Or as I said, we could write it this way. It depends on what technique you use. So we could say minus V1 plus I1 R1 plus I1 R3. And then we find the contribution of I2, which is minus I2 times R3 equals to 0, which is similar to this one here, similar to this here. Okay, so just if we FOIL this one, multiply R3 times R1, we get this one here, and minus I2 R3 is the same. And then we can reorganize the this equation here by having the I1, so R1 plus R3 times I1. Just gather the similar terms, I1, R1, and factor out I1, take I1 out. And then for I2, we only have one term, so it will be I2 multiplied by R3. And then we move V1 minus V1 to the other side, it will become my V1. So this is equation number one. So now, since we have two meshes, we must have two equations. When we have two equations, then we will be able to solve for I1 and solve for I2. This is our objective here. Our objective is to find the mesh currents, I1, I2, I3, and I4. Again, depends on how many meshes do we have in the circuit. Now, for mesh number 2, I say I'm going to apply KVL. For mesh number 2, I could use the same technique as the book, or I could use, the whatever technique you use by just going one by one. So since we are using loop number 2, so I2 will be multiplied by R2, so it will be a positive because the current is moving from the higher, from this side to that side, so this has to be a plus, this has to be a minus, and the same thing for R3, so the bottom will be a plus and the top for I2, okay? So now we are just focusing on I2 because we are finding, or we are applying KVL around loop number 2 or around mesh number 2. As you know, sometimes I said it a loop, sometimes I said it a mesh, because a mesh is a loop. Okay. Also, because the definition of the loop is a complete path. So this will be I2 R2 plus I2 plus I2 R3. Now we need to find the contribution of I1, which is negative, because it's in the opposite direction of I2. So it will be a negative I1 R3 equals to 0. Or you could use this way. So we could go I2 times R2 plus I2 minus I1 multiplied by R3 equals to sorry, it's equal to plus, I did a mistake here. I forgot to put the voltage here, so it will be a plus V2. Now again, why is a plus? Because the current is hitting, the I2 is hitting the plus sign of the V2. So this will be I2 minus I1. Okay, so we have I2 going up and I1 going down, so they are in opposite direction. And then we have minus V2, because when I move V2 to the right hand side, it will become a plus. Now again, I need to rearrange this equation to have, the same order as the first equation. So I have to have I1 first, then I2 second. So I have to have here minus I1 minus I1 R3, okay, and then plus R2 plus R3 I2 I2. Okay, let me rewrite the equation here because I don't have enough space. So let me take off all of this here and rewrite the second equation after I rearrange it. So it will be minus I1. Let's change the color here. So it will be minus I1 R3, and then we have plus R2 plus R3 I2. That will be equal to negative V2. Okay, so this will be our second equation. So after that, if we have the value of R1 and R2 and R3 and the value of V1, V2, then we can use one of those techniques, either the Cramer's rule, which is a matrix method, or the substitution method, or the elimination method to solve for I1 and I2. And after solving for I1 and I2, we'll be able to find I2 flowing through the resistance R2, and also to find the current flowing through the resistance R3, which is I3, and the current flowing through the resistance R1, which is I1. If we know that, then we'll be able to find the voltage across the resistance, V1, and the voltage across resistance V2, and the voltage across resistance. Okay, so we know I3, we know I1, we know I2. We'll be able to find V1, V2, V3, and also we'll be able to find P1 and P2 and P3. Okay, so again, it's just a way of how to determine this currency. Okay, so let's look to this example 7.1. So what we have here, we have all the elements value, we have the voltages here. So we need to apply. So the first thing, if we are not having the current assigned, okay, let's say that I1 and I2 are not assigned. So then we can assign the mesh currents in clockwise. Now, should I do that? You don't have to. You could assign them, clockwise, both meshes, or counterclockwise, both meshes, or one clockwise, one counterclock. So it depends on, whatever but usually people, they like to have the assigned mesh current in the clockwise direction. Okay, so now we need to apply. So the first step to assign the current, the mesh currents. If not, if they are already there, then we move to step number 2. Step number 2 is to apply KVL around the two meshes. So let's start with the 15. So it will be minus 15 plus Now I1 times 5, so it will be 5I1, and then will be 10I1 plus 10I1, and then will be plus 10, okay, the voltage here is 10, okay. Now we need also to include the voltage drop contributed by the current I2 here, okay. So what is the contribution voltage drop of I2? Will be a minus. Why is a minus? Because it's the opposite, or and it has an opposite direction of current number 1, or I1. So it will be 10 I2 equals to 0. Again, we could combine the 5 and the 10, would be 15 I1 minus 10 I2 equals to, we have minus 15 volt and 10, so it will be minus 5. Move it to the other side, so it will be 5 volt. Okay, so this is number 1, equation number 1, which is similar to what the book has. So this label, this is 1. And then again, if you want to use the same way as the book, you could start with the minus 15 plus 5I1. And then when you come to the resistance that it's in between the two loops or two meshes, then we start with the I1 minus I2. Do not start with the I2, because now we're applying our KVL around loop number 1. So loop number 1 means I1. So I1 has to be first minus I2, and then multiply by 10, and then we have to add the other voltage, which is a plus 10, equal to 0. And then you organize rearrange this equation. You will end up having equation number 1. Okay, so this is one way to do it, or there's two ways to find out the final first mesh equation. Now the second mesh equation, again, we need to apply KVL around mesh number 2. Again, the same way, it doesn't, where do we start? So let's start with the 6 ohms. So it will be I2 multiplied by 6, and then it will be 4 multiplied by I2, and it will be minus 10. Can again see the current here flowing this way, so it hits the minus sign. So let me take off this here. Okay, so we have minus 10. And then when we come to the resistance 10, okay, the resistance 10, again, it will be plus I2, okay? See, when we wrote the KVL for loop number 1 or mesh number 1, we use I1 minus I2. Now, since I'm applying KVL around mesh number 2, so I have to use I2 minus I1 multiplied by 10. Okay, equals to 0, and then rearrange the equation. So we have 10 I2, and then we have minus 10 I1. So I have to put it first because I need to organize in the same manner as equation number 1. So we have to put I1 first, since I have 15 I1 in equation number 1 first. And then we have the I2, we have 6 I2, and then we have 4 I2, and then we have 10 I2. So we have 20 I2 equals to 10 volt. Okay. So this is what we have here. Now the book here, it doesn't, the book here exactly as this one here, use the same way. So this is equation number 2. Now we need to solve. We need to solve for I1 and I2. So now we need to go to the algebra, to the math. Now again, there's 3 methods to use to solve for I1 and I2. One of them is using the substitution method here. Substitution means we can either use equation 1 and find I1 in terms of I2 and then substitute the equation of I1 into equation number 2, so we have only one element. So let me erase some of this here so I have enough space to solve. So, okay, so here's my two equations. I'm going to rewrite my two equations. It will be 15I1 minus 10I2 equal to 5. And then I have my second equation will be minus 10I1 plus 20I2 equals to 10. Okay, so this is equation 1, this is equation 2. So we could say from equation 1, I can find I1 is equal to 10I2 plus 5 over 15. Okay, so we used equation number 1. So we take minus 10 to the other side, become a plus, and divide by 15 both sides. So this one will be 5I2 plus 1 over 3. This is I1. Now I substitute for I1 in equation number 2 here. Okay, so in this case, I will have only one term or one symbol here, one variable, I2, and then I can solve for I2. So it will be minus 10, and then substitute for I1 will be 5I2 plus 1 over 3 plus 20 I2 equals to 10. Okay, so if we multiply both sides by 3, so we have minus 50 I2 plus minus, let's put a minus here, minus 10. Okay, I'm going foiling the 10 here. After multiply both sides by 3, multiply by 3. Well, you have to multiply by both sides. You cannot just multiply by the left-hand side without multiplying the 3 by the right-hand side. So 3 times 20 is 60 I2, and the right-hand side will be 10 times 3 is 30. So now I can add, subtract the 50 from the 60. So we will have, let me see here, we have 60 I2 minus 50 will be 10 I2 equals to, now I can move the minus 10 to the other side and it will change the sign. Or sometimes, mathematicians, they use adding the plus 10 in both sides same way. So this will be a 40. So now we have I2 will be equal to 4 amps. Now, after finding I2, then we can go and we plug the value of I2 in here to solve for I1. Okay, so to solve for I1, we said I1 equals to 5 times I2, which is 4 plus 1 over 3. So this will be 20 plus 1 is 21 over 3 will be 7 ampere. Okay. So again, this is one way. This is called the substitution method. Now the second method is the Cramer's rule. Okay. So let me just erase this one here. Let me see, I think I might. Sorry, Guy, I think I did a mistake of the solution. Let me redo the solution one more time. So the two equations, we have 15I1 minus 10I2 equal to 5. You could divide by 5 both sides. And equation number 2 would be minus 10I1 plus 20 I2 is equal to 10. So let's take equation number 1 and find I1. So I1 will be 10 I2 plus 5 over 15, or it will be 2 I2. I think this is my mistake here in the previous solution. Plus divide by 5 will be 1. 15 divided by 5 will be 3. Now I need to substitute the I1, this equation, into equation number 2 here. So we will have minus 10, and then 2I2 plus 1 over 3, and then plus 20 I2 equal to 10. So again, to get rid of the 3, just multiply both sides by 3. So we get 3 divided by 3 is 1, so we'll get minus 20 I2 minus 10, and then 3 times 20 is 60 I2, and 10 times 3 is 30. Now, plus 60 and minus 20 is a 40 I2 equal to, and then the 10, we'll move it to the other side. It become a plus 10 plus 30 is 40. So therefore, I2 is equal to 40 over 40 is going to be 1 amps. Okay, now we go back here and we plug for the value of I2 to determine I1. So I1 is equal to 2 and times 1, I2 is 1, plus 1 over 15. So over 3. This will be a 3, so 3 over 3, so I1 is equal to 1 amps, which is the same as solution in the book here, okay? Okay, so we're done with this method here. Now, if we need to use what we call the Cramer's rule, this method here. So this method depends on a matrix, okay? So we need to just explain a little bit more how to find the determinants of a matrix, which is delta. So to have this format, okay, first we need to convert the two equations in a matrix format, okay? So we have 15, let me write down the two equations we have equal 5, and the second one will be minus 10 I1 minus 10 minus plus 20 I2 is equal to 10. This is the two equations I have. Now I need to put these equations in, so put this equation in matrix format. Okay, how we do that? We just open a bracket, another bracket, equal sign, another bracket. So what we put in the first bracket, we put the coefficients of the left-hand side. So it will be 15 minus 10, then minus 10, then 20. And in this small bracket, we put I1 and I2, the variables. And the right-hand side bracket, we put the value of the equation, the right-hand side. Okay, so this is exactly the same, but I think the book he divided by 5. So 5 divided by 15 divided by 5 is 3. So we can simplify this here, it will be easy for calculation. So it will be 3. So we divide all the elements by 5. So this will be 2, and this will be and then the second equation we divide by 10, so it will be minus 1. 20 divided by 10 is 2. And I1, I2. And the right-hand side, again, since we divide the first equation by 5, so it will be 1, and this one will be 1. Okay, so the first equation divide by 5, because there's a common value, and then the 10 is a common, so we divide by 10 both sides. So this is our, so to do the solution, so we need to find delta. Delta is the determinant of this matrices, which is 3 minus 2 minus 1, 2. Now, to find determinant, so always we do the cross multiply. Let me change the color. Okay, cross multiply, so multiply 2 times 3, and then subtracted from minus 1 times minus 2. Minus 2 minus 1. Okay, so this would be 6 minus, and then minus minus is a plus, plus times minus is a minus, minus 2, so it will be 4. Okay, so we need this value. That's the first thing we need to do is to, so let me write down delta here is equal 4. Let me erase the delta. Okay, so this is the first one. Okay, before I forget, let me write down delta is equal to 4. Now I need to find delta 1. What is delta 1? Delta 1, I replace the right-hand side column and put it on the first column of the matrix. Okay, so it will be 1, 1, minus 2, 2. So we keep this the same. Okay, so we replace. Can we take this out, remove it, and put this instead? And then use the rules of the determinant. So we multiply, cross multiply like this with the minus sign. So we said 2 times 1 minus sign here, and then 1 times minus 2. So it will be minus 2. Okay, so this will be 2 plus 2 is equal to 4. So again, delta 1 is equal to 4. Now we move to find delta 2. So delta 2 will be replacing the second column of this matrix here by the right-hand side column. Okay, so it will be delta 2 is equal to, so we keep the same column of the matrix, 3 minus 1, and we replace the second column by the right-hand side column. So it will be 1, 1. Again, to find the determinant, we do the cross multiply, 1 times 3 minus 1 times 1. Okay, and again, here's the cross multiply with the minus sign. Okay, so 1 times 3 minus multiply by 1 times minus 1. So it will be 3. Now we have 1 minus 1 times 1 will be a 1. So it will be plus 1 will be 4. So all the 4. Now to determine the value of I1, so I1 is equal to delta 1. So I1 is equal to delta 1 over delta. And I2 will be delta 2 over delta. So same thing, delta 1, I1, delta 2, I2. So delta 1 is 4, that's 4, it will be 1 amps. And this one will be 4 over 4 will be 1 amps. So again, either solution, whatever you pick, it's fine to do that. Okay, I'm going to give you a hint here how to calculate the I1 and I2. So I'm just trying to help you to write the two equations. So we start with the first one, minus 12 plus 2 I1 plus 12 I1 plus. Now if you want to use the book method, let me go back and keep the middle one at the end, so it will be 2I1 and then it will be 4I1, and then for the middle one it will be I1 minus I2. Let me put this down here. Okay, so then this, the middle term here, or the common resistor between the two meshes, will be I1 minus I2 multiplied by 12 equals to 0. Okay. Now again, if you want to do the other way, just to do I1, 2 times I1 plus 12 times I1 plus 4 times I1, and then negative minus 12 times I2. Okay, and then you move the 12 to the other side, and then you collect the similar terms. So the similar terms, so the final equation will be, we have 2 and 4 and 12. So we add 2, 12 is 14, and this is 18. So it will be 18 I1. So again, 2 and 12 is 14. 14 plus 4 is 18. And then for the I2 will be a minus 12 I2 equals to minus 12. So again, equal to 12, so plus 12. So this is equation number 1. Now equation number 2, it will be, again, we have 9 and 3, so it will be 12 I2 minus 12 I1, and then plus 8 equal to 0. And then reorganize the equation, so it will be minus 12 I1 plus 12 I2 equal to minus 8. And then use one of those techniques to solve for I1 and I2. Now this one, again, it's, I help you to, this is the example here, how to write down the three equations. Just use the, I'm not ask you to solve the, the tree loop, because it's a little bit harder. So I'm going just to show you how to determine, how to find the three equations, the three mesh equations. So let's start with the first one. So it will be minus 24 minus 24 plus I1 times 10 I1 plus. Now, again, if you want to use the book technique, you could combine, you could say I1 minus I2. Let's do that. Okay, I1 minus I2 multiplied by 10. And then for this resistor here, because it is a common between mesh 1 and mesh 3, so it will be I1 minus I3 multiplied by 12 equal to 0. And then you can, you can collect the similar terms in one side and the number on the right-hand side. Now for the second loop, or mesh 2, we could use, let's start with 24. So it will be I24, I2, and then because this is the middle between loop 2 or mesh 2 and mesh 3, so it will be plus I2 minus I3. So again, I'll just remind you why did I start with I2 first? Because I am writing or applying KVL around mesh number 2. So I2 will be the plus. when I apply KVL around loop number 1, I use I1 with a plus sign. So say I1 minus I2, I1 minus I3 times 12 and so on. Okay, so it will be I2 minus I3 multiplied by 4. And when we come to the 10 ohm, same thing will be plus I2, it's not I1, minus I1 multiplied by 10, okay, equals to 0. Okay, and then you can collect the similar term. Okay, let's do the third one. So the third one will, let's start with the 16. So it will be a plus 16. And then this is the common. So it will be I plus I3 minus I1, because I'm applying KVL around loop number 3. So my I3, it will have the plus sign, minus I2, so the I2 is the neighboring mesh. I3 minus I1 times 12, and then for the number 4, same thing will be I3 minus I2 multiplied by 4 equals to 0. And then we can again rearrange the equations and have I1 first, then I2, then I3 equal to negative 16. So you will have the the equations, the 3 equations. Okay, let me also give you a hint of how to write these equations. So again, I'm not asking you to solve the 3 by 3. I just ask you only to solve 2 by 2. So since this practice problem and the previous example are 3 equations, so I'm not asking you to solve for the currents I1, I2, and I3. The only thing I will ask you is to find or determines the 3 mesh equations. So what are the 3 mesh equations? So let's start with I1. So again, it will be 2 times I1 plus now 4. So the 4, because it is a common between, it's a common between I1 and I3. So it will be 4 multiplied by I1 minus I2. And then same thing, this is I3, sorry. And then the same thing for the common 2 ohm resistor between mesh 1 and mesh 2. So it will be 2 multiplied by I1. So that show I1? Yes, I1, because my applying KVL around loop number 1. So I1 has to be a plus, minus I2 equals to 0. Sorry, I should finish the voltage here. So the voltage is minus 20 equal to 0. And then you can move the 20 to the other side, and then you could reorganize. You combine the similar terms. So let me do this for you. So we have I1 and 4I1 and 2I1. So in fact, we have 4 plus 2. Okay, so I did a mistake here. I shouldn't have this one here, since I'm using this technique here. Okay, so I have 4 and 2, so it will be 6 I1, and then it will be minus 2 I2 and minus 4 I3 equals to 20. Okay, so this is equation number 1 for mesh number 1. Okay, let's do equation number 2. So we have I2, so it will be 8 I2 minus I3, it doesn't matter where you start, you know, plus 2 multiply 2 times I2 minus I1 plus 10 equals to 0. Now you might ask why we don't use the 4. Well, 4 is not a common, so I2, it doesn't flow through the 4. It's only the current I2 flows through the 2 ohm resistor and the 8. Same thing when we apply KVL around loop number 1, I did not include the 8 because I1 is not flowing through the 8 ohm resistor. Okay, and to reorganize that, so it will be minus 2I1, then plus 10I2, and then minus 8I3 equals to negative 10. Okay, so this will be a second equation for the second mesh. Okay, for the third one, which is this one here, so let's start with the 6, so it will be I6, I3, and then we have I3 minus I2 times 8, then plus I3 minus I1 multiplied by 4 equal to 0, since there's no voltage, supply voltage in this loop. So again, if we need to rearrange the equations, similar terms, we will have, you know, 18 I3, and then we have minus 4I1 and minus 8I2 equal to 0, or as I mentioned, you should organize this equation one more thing to put negative 4I1 first, and then 8I2 second, and then 18I3 equals to 0. And so these are the three equations we need to solve. But again, I'm not requesting you in this course to solve for 3 by 3. The only thing I want you to know and to understand is how to solve the 2 by 2 equations, or 2 equations simultaneously to find I1 and I2. Okay, in this example, again, we will, this is a little bit tricky here. I'm going to show you how to deal with, this is called dependent voltage source, which is dependent on Ix. So I'll show you how to substitute for Ix. So let's write down, or let's apply KVL around mesh 1. So it will be minus 10, and then plus 4I1, and then minus 2Ix, okay, minus 2Ix, minus 2Ix, and then minus, then plus 6I1 minus I2 equals to 0. Now, how to substitute for Ix? Because if I keep Ix, then I will have 3 unknowns. I have I1, I2, and Ix. Now, if we look to the Ix here, so we can find Ix in terms of I1 and I2. Since Ix moving down, so that means it moves with the same direction as I1. So it will be I1 minus I2. So now I can substitute for Ix is equal to I1 minus I2 in this equation here, and then collect the similar terms of the So let's do that here, have more space here. So it will be minus 10 plus 4i1 minus 2, open parentheses, and then plug for ix, which is i1 minus i2. Okay, so I already plugged for ix, and then plus plus 6i1 minus 6i2 equal to 0. Okay, let's put this. Okay, so let's rewrite this one more time. So it will be, so we have 4i1, let's put 4i1, 4i1 minus 2i1 plus 2i2. Remember here minus 2 multiplied by minus, so minus plus multiplied by minus is a plus, 2 times i2, and then plus 6i1 minus 6i2 equals to 0. Actually equal to 10, so because I have to put the 10. So always the number has to be moved to the right hand side. Okay, so we can collect the similar terms. So we have 4i1, and then we have 6i1. This is 10, 10 minus 2, so it will be 8i1. And then we have 2i2 and negative 6i2, so it will be negative 4i2. And this will be equal to 10. Okay, so this will be our equation 1. If we want to simplify equation number 1, we could do that by dividing both sides by 2. So it would be 4i1 minus 2i2 equal to 5. Okay, now let's move on to find the second mesh equation. So this mesh here, we'll start with the 2, so it would be 2i2 plus 12, and we have 6 here will be I plus I2 minus I1 multiplied by 6 equals to 0. So that means we will have to simplify this equation. We have 8i2, 8i2, and we have negative 6i equals to negative 12. So the 12 goes to the right hand side. We change the sign because it was a plus. And then we have 6i2 plus 2i2 is 8. And then we have negative 6i1. So this is the second equation. And again, we could use one of those techniques to find the I1 and I2. In this practice, I will show you how to find the two equations, and then after you find, so in this case, we have to assign the loop or the mesh currents, I1 and I2, and then we start applying. So I said apply KVL around loop 1 or mesh 1, around mesh 1 and 2. So let's do the first one. So it will be minus 24, then plus 2i1, and then plus 3i1, and then plus 4i1 minus i2 equals to 0. Okay. So here's i1. We have 2, 4, and 3. So we have 9i1. And then negative 4i2 equals to 24. So again, we have 2i1, we have 3i1, this is 5, and then we have 4i1, this is 9. And then we have 4 times negative i2, so this is equation number 1. Now to do the second loop, so let's start with the 5, so it will be 5 i2 plus 3i2 plus 6ix, okay, and then plus 4i2 minus i1 equals to 0. So again, because we are doing it for loop number 2 or mesh number 2, so i2 will be a plus. When we do the apply KVL for current i1, so current i1 will be a plus. Okay, now the only thing I need to just to find out is the ix in terms of, so ix, if we look to ix, it's going from, so ix actually is the same as i1. Okay, so is ix going this way? So that means, so remember when we have an ix in this direction in the 4, because in the 4 ohm, we have 2 currents flowing in the opposite direction. So the total current will be I1 minus I2. Now, but for this one here, the only current flow through the 2 is I1. So Ix is equal to I1. Now we plug for Ix is equal to I1. And then we collect the terms. So we have 6 and negative 4 I1. So it will be negative, plus 2 I1, and then for I3 would be I2, sorry, would be 5 and 3 and 4. So it would be 8 and 4 is 12, plus 12 I2 equals to 0, because you don't have any voltage source with a number here. Okay, this is, we call this as dependent voltage source. That symbol here, the diamond symbol, it means that this is not voltage supply. This is just a symbol that tells you that this voltage here, it depends on the current flowing in the through 2 ohm resistor. And if you multiply that current by 6, they give you a value here. So this is like a voltage drop. Okay, so again, let's check one more time. So we have 5I2, we have 3I2, and then we have 6ix, and ix is I1. And then we have 4I2 minus I1. So this is 6I1 minus 4I1 would be 2I1. And then we have 5 plus 3 is 8. 8 plus 4 is 12. So this is the second equation. Again, you could use one of those techniques to solve for I1 and I2, and then we need to find VO. Now VO is equal to voltage drop across the resistance when we applying Ohm's law. So to find VO, we need to apply Ohm's law. So V0 is equal 5 times I2. because the current flowing here is I2. Remember that? We assume it's I2 going this way. So it will be whatever the value of I2, we just plug for the value of I2 to find V0. Okay, what happened if we have in one of the meshes, we have a current source? Is it going to be helpful? Is it going to be simpler when we analyze the circuit? The answer is yes. If we have a voltage, a current source in one of the circuit, as far as the current source is on the side, it's not in the middle here, okay? If we have a current source in the middle, that will be a problem. We are not going to cover this one. We're going to cover only if we have a current source either here or here or here or here or here or here, just on the side, not in between the two meshes here. So for this case, when we write the KVL for I2, so I2 basically will be equal to -5. So actually, if we have a current source on the side of the mesh, actually will give us one of the solutions. So it will be even easier than the previous case when we have this is a voltage source, or both meshes have a voltage source. So again, if the current source is located on only one mesh, the current for that meshes is defined by the source. For example, the current I2 is equal to should be -5. That should be -5. It's a typo mistake. Okay, so let's see how to, now it seems here in this example that we have 3 meshes, which means we have to solve for 3 equations. But in fact, we only solve for 2 equations. Why? Because I3 will be given. Because I3, it has, or the mesh number 3, it has a mesh, or it has a current on the side. Okay, so in this case, I3 will be equal to 5. Now, why is not a minus? Because we assuming, or we having, the current direction of I3 is the same as the current direction of the supply, or the source, current source. So this is called the current source, this is called a voltage source. These are voltage source. Okay, now we go back to our technique. So we need to find V0, so we need to find I1 and I2 because the voltage here across the resistance is equal to the voltage across the resistor here. It's 4 times the current here through the 4 ohm resistor. Now the current here is I1 minus I2. Okay, why I pick times, this would be I going through the resistors, the difference between I1 and I2 going up, I1 going down, so it will be I1 minus I2. Then we multiply that by 4, because Ohm's law said if you need to find the voltage, you need to know what's the current going through that resistor, multiply by the resistance value, you get the voltage. Now, why did I pick I1 minus I2, not I2 minus I1? Because see the plus sign here, it indicates that the current I1 going down, and since this is a plus, then we have to start with the I1. If I switch, for example, if I switch the polarity of V0 to make it a plus and a minus, then because I2 is hitting the plus, so the I2 has to be a plus, and I1 is going to be the minus because it's hitting the minus. So this is how you figure out the current which current start first when we determine the voltage across the resistance. Okay, so for equation number 1, as stated here, we have minus 40, okay, minus 40, and then we have I1 times 1, and then we have I1 minus I3. We multiply this by 2, and then we have plus I1 minus I2. We multiply this by 4 equals to 0, and then we organize the terms. We have 7I1 minus 4I2 minus 2I3 times 4 equal 4. Now, that's equation number 1. Okay, now equation number 2, or for mesh number 2, we will do the same thing. Let's start with the minus 20 here, and then we go down here is a plus I2 minus I1 multiplied by 4, and then for the 8 it will be plus 8 I2 equals to 0. Okay, so same thing here. We have minus 4I1 plus 12I2 equal to 12. Now for mesh number 3, so because see the current here, okay, so we don't do the KVL, we don't multiply 2 times I3, we just find that I3 is equal to 5 amps. So this is already being determined. So now we go back here, whenever we have I3, we plug it for value 5, and then we can have equation number 1. So now we have to say, so this is for mesh number 3, okay? So mesh number 3, you don't need to apply KVL. You just need to find what is the value of the current source. That will be equal to I3. So if 5 is going this direction, then I3 will be a negative 5. But since we have the current flowing in the same direction as I3, so I3 will be a plus 5. Now, substitute equation 3 into equation 1 here, okay? Because we don't want I3 here, okay? We only want I1 and I2. So actually this example or this circuit only has 2 meshes to solve, or 2 equations to solve. So these are the equation number 3 and equation number 2. These are the 2 equations that we need to solve to determine for I1 and I2. So again, I will show you here the 3 methods that we need to use to substitute. So substitution method, again, we could use equation 2 to find I1. So I1 will be 20, will be 12 I2 minus 20 divided by 4. So this will be the I1. And then we go and substitute for I1 is equal to 3, or substitute equation 4 into equation 3, and we will determine I1. Will determine I2, so because we will get rid of I1 here, 7 multiplied by 3I2 minus I1, so then we have I2 equal to 5. Now the other method is the elimination method. I'm going to explain this one because I haven't talked about it before. So the elimination means I will find the way to eliminate one of the variable, either I1 or I2. Now the easiest way to eliminate is to eliminate I2. So if I multiply equation 3 by 3 to make it equal to 12, and then add the result to equation number 2. So if I multiply equation 3 by 3, both sides, so it will be 21 I1 minus 12 I2 equal to 150. So again, I have to, so this is the new equation after I multiply it by 3. Now, if I add this equation, the 21I1, this is 21I1, 21I1 plus 12, minus 12 minus 12I2. Now, then my first equation or second equation, minus 4I1 plus 12I2 equal to 20. The reason I multiply this, the third equation by 3 is to make it similar to the 12. So now if I add these two equations, what the result will be, so it will be 17I1, so 21I1 minus 4, and then this will be eliminating because plus 12 minus 12 is 0, equal to 170. And then divide by 17, so I1 will be 170 over 17 is equal to 10 amps. And then after I find the I1, I go to the one of the equations. So then use either equation 2 or 3, whatever the one that you feel is easy to use, and then find. So to solve, let's use equation 2. So this is equation 2. We have to find I2. So I2 will be, so 12I2 equal to 20 plus 4I1. So again, this equation leads to this equation here. So divide by 12, so I2 would be 20 plus 4, and then we have I1 is 10 divided by 12. So this will be equal to 5. So, okay, so this is how to solve the equation by elimination. So now we cover the three methods, the substitution method, the elimination method, and the Cramer's rules or the matrix method. This is also has to be 2. Okay, let me move to the next slide. Okay, next slide. Let me erase this one here. Again, this is, don't scare from this one. So mesh number 1, you just apply KVL. Mesh number 2, I2 is equal to -3. Okay, and why negative? Because I2 is in the opposite direction of 3. Okay, so again, actually, we only have one equation to solve, which is the equation of mesh number 1. And to do that, we just do 8I1, 8 times I1 plus 2I1 plus 2, and then 4I1 minus I2, and I2 is equal to -3. We just plug 4. Okay, so for right, so and then this is the equation for right hand side. Now I2 is equal minus I3. We plug for that, would be 14I1 minus 4 minus 3 equal to -2. So this would be 14I1, and this is would be a 12 equal -2. Okay. So that would be, so I1, so it will be 12. So 14I1 equal to -14. So I1 is equal to -1. Now, what is the meaning of a negative? So that means our assumption of the current direction is not right. So in order to make it real, so we can just say that, we change the direction If we switch the direction, then the result I1 will be equal to 1. Okay, but again, it's, the negative sign mean that the current I1 should be on the opposite direction. Okay, Kramer's rule. Here I give another example of how to use the Kramer's rule. So you can go over this and you can use this technique. Again, sometimes this technique, especially for 2 by 2 or for 2 equation, is maybe simple, but again, it's very important how to write how to put the 2 equations in the matrix form. So again, you take the coefficient. So that's why it's very important to have I1 and I1 here, I2 and I2, and the right-hand side. So you need just to open a bracket here, and you put those 2 coefficients underneath, and these 2 here underneath, and then I1 and I2, and then the right-hand side would be 50 and 20. Now the order of the, if you flip the order, you put -1 I1 plus 12 I2 equal to 20, and you put 7 I1 minus 4, 7 I1 minus 4 I2, the result will be the same, minus 4 minus 4 I2 equal to 50. So it will be the same. The only thing, just when you transfer this to the matrix, you put it in the same order. It will be minus 4, 7, 12, and minus 4. Okay. Just swap these 2 columns. Okay, and then follow the rules of how to find the determinant D and D1 and D2, and then to find I1, you take delta 1 over delta and delta 2 over delta to find I2. Okay, nodal analysis. So if instead of focusing on the voltage of the circuit elements, one looks at the voltages at the nodes of the circuit, the number of the simultaneous equation to solve for can be reduced. Given a circuit with an N node without voltage sources, the node analysis is accomplished via 3 steps. Okay, so these are the 3 steps to determine or to analyze the circuit using the nodal analysis. Select a node as the reference node, assign voltage V1, V2 until the end of the nodes to the remaining N-1 nodes. Voltages are relative to the reference node. I will explain what is the relative node, the reference node. Apply KCL. Now, in the mesh analysis, we apply KVL. In the nodal analysis, we apply KCL to each of the N-1 or the non-reference node. So now we have 2 names, a reference node and a non-reference node. I will explain this later. Use Ohm's law to express the branch current in terms of the node voltages. Solve the result N-1 simultaneous equations to obtain the unknown node voltages. So in the case of the mesh analysis, we solve for the mesh currents. Now in the nodal analysis, we solve for nodal voltages. Now the reference or the datum node is commonly referred to as the ground, since its voltage is by default 0. So this is the definition of the the reference node. So the reference node usually is the negative terminal of the power supply connected to the ground to be sure the voltage of that point of the negative side of the power supply to be zero. And they call it the reference node. Okay. So in this case, as we see here, the reference node is this one here. Now, this is a node, this is a node. So these are called a non-reference node. Okay, so this is a reference node. This is non-reference node. So the number of the equations in the nodal analysis, it will be equal to the number of the non-reference nodes. So in this case, since this is node number 1, this is node number 2, these are a non-reference node, which means they are not connected to the reference node. They are not connected to the ground. So between node number 1 and node 0, there is an element. And also between node 2 and the 0, there is an element. Now these are called nodal voltage. So this will be V1 and this will be V2. So the nodal voltage is the voltage between that node, number 1, with respect to the ground. And V2 will be the voltage between this point and the ground. So in other words, it will be the voltage between the node 2 and the ground, or the voltage across R3. V1, or the nodal voltage V1, is the voltage across R1. Now the voltage across R2, VR2, it will be V1 minus V2. Now the voltage across R1, VR1, it will be V1 minus 0, because this voltage here, it's a 0. It's a reference, it's a ground. Now VR3, also it will be V2 minus 0, or in general, it will be V2 or V2. So again, always the voltage across the resistance, it will be where is the current flowing. So the current starts from the node number 1 going down. So always we start with that voltage, with that point V1, minus the voltage where the arrow going to. Now same thing here for the I2. We see here I2 is going this way. So the voltage VR2, it starts from V1, because we are assuming the current through the R2 is going from left to right. So this is always a plus, this is all minus. So always the voltage V1 is higher than the voltage V2. If we assume the current going from V2 to V1, then VR2 will be V2 minus V1. So again, it depends on the direction of the current. So again, as we did in the mesh analysis, we assign the mesh currents. Here we assign the nodal voltages. So we assign V1, assign V2. That's step number 1. Assign the nodal voltages. Step number 2, assign current directions. Okay, they call it the element or the branch currents for R1 and R2 and R3. Now, is there any way that we assume the current direction? No, you could pick any direction you want. But many people, they prefer to assign the current. If the element is in the horizontal, they prefer to assign the current going from left to right. And if the elements are vertical, like R1 and R3, so they assign current going from top to bottom, like in here. Okay, so from left to right for R2, up top to bottom for R1, top to bottom for R3. Okay, so again, 2 steps you need to do before you start applying KCL. Assign the non-reference node, the nodes that are not connected to the ground. And then the second thing, assign the current direction that passes through the resistors. These currents here, I1 and I2, they already been assigned for their direction, so you cannot change them. And then after that, the step number 3 is to apply the KCL to each node. So now if we apply KCL at node number V1, so we have that I1 is, we know that KCL, current entering a node, or currents entering a node, equals currents exiting or leaving the node. Okay, now if you look at the node V1, we have I1 is entering the node, so I1 is entering the node, and then we have I2 uppercase and I2 lowercase and I1 leaving the node, so the left hand side will be I1, which is current entering a node, is equal to I2 plus I1 plus I2 lowercase, which is the same as this equation. Now, applying KCL here, we see that I2 is entering the node, uppercase. I2 lowercase also is entering the node. I3 is leaving the node. Okay, so 2 currents are entering, which is I2 plus I2 lowercase equal the current leaving the node, which is I2. Okay, so again, then we establish 2 equations. So these are 2 equations to solve. Using the same technique as we explained in the mesh analysis. Okay, then the next step is to apply the Ohm's law. Okay, let's go back to the previous one here. So we have I1 equal I2 plus I1 plus I2 lowercase. And then we have I2 is equal to plus I2 equal to I3. Now we need, after we apply KCL, now we need to apply Ohm's law, which means I want to convert I1, I2, and I3 lowercase in terms of the nodal voltages. That's why we call the nodal analysis. So nodal analysis is to solve for the nodal voltage. Mesh analysis is to solve for the loop or the mesh currents. Now, to find the I1, we know I1 is the current. If we apply Ohm's law, it is a voltage over resistance. Okay, so I1, what voltage is of I1 here? So I1 is going through R1. So the resistance has to be R1. Now the voltage going from V1 to the non-reference to the reference node. So V1 is V1 minus, what is the voltage here? It's a 0. Same thing for I3. I3, the current goes from V2, so start with a V2 minus 0. So always to find the current through a resistor, we must find the current difference of the voltage difference or the voltage drop between where is the current starting to where is the current going to. Current goes from V2 to 0. So that means V2 minus 0 over 3 here. So we're done with the I1 and I3. Now for I2 equal the voltage drop across which is VR2 over R2. Now, what is the voltage drop across R1? Is the voltage V1 minus the voltage V2 divided by R2. Now, V2 is not zero because it's a non-reference node. But in the case of I1 and I3, so always, this is the rule of thumb. If you have a resistor, you have a voltage here, V1, you have voltage V2. If you want to find the current I through that resistance, I1 and R1, to find the current I, according to Ohm's law, I1 is equal V across the resistance, R1, divided by the resistance. Now, the voltage drop across R1 is not just the V1, or it's not just the V2, it's the difference between. It's V1 minus V2, that would be the voltage drop across R1, divided by R1. Now, why we start with the V1, not with the V2? Because I1, I assume going from this point, which is a plus, minus to the minus point, which is a minus here. Okay, so this is, now if I assume the current going this way, and I need to find I1, so in this case, I1 would be V2 minus V1 over R1. Okay, so again, this is a rule of thumb that you need to know the current direction. Again, these directions, the red one, we assume. You can assume in any direction you want, but it's much easier to assume the current going from the top, bottom, left to right. Okay? But again, you could assume from bottom to top. But again, you have to be careful, because if you assume the current going from the bottom to the top, then it will be I1 or I3 in this case, and be 0 minus V2 over R3. Okay, so we have a minus. So it's not a plus as we did if we assume the current. We say V2 minus 0, so it's a plus V2. Now, if you assume the current going up, it would be 0 because the voltage here is 0 minus the voltage. So always you start from the tail of the arrow to the spear of the arrow. Okay, for I2, so now if we plug, so I1 and I2 uppercase, this R will be a value. So we'll say I1 equal to I2 plus I1 plus, now I1 we said V1 over R1 plus I2 we said I2 is V1 minus V2 over R2. Okay, this is the first. Now, so now we have the equation in terms of V1 and V2, which are the nodal voltages instead of currents. So when we do nodal analysis, again, we have to convert currents into voltages using Ohm's law. And then for the second equation would be I2 plus I2 lowercase equal to I3. So again, I2 is a number plus I2. Again, we already had I2 before. So it will be V1 minus V2 over R2 equal to I3 will be V2 minus 0 over R3. So again, you could eliminate the 0. Okay, and then so these are the two equations in terms of the nodal voltages. Then we can solve the two equations using one of those techniques that we had before. Okay, let me see what is the next. Okay, so let's see here how to calculate the voltage in the circuit. So how to find V1 and V2. So again, sometimes those numbers won't be given. So you have to look for the nodes here. Okay, so we have two nodes here, We have how many elements here? We have 1, 2, 3, 4, 5 elements, and we have 2 non-reference nodes, and this is a reference node. So always a reference node has a 0 voltage. Non-reference node has a value. We don't know until we solve the problem. So first step, what we need to do, we need to assign the voltages V1 and V2, V1, V2, and assign currents. Again, assign currents, this has already been assigned, this has already been assigned. Now, top to bottom, left to right, as in here. Okay, so again, this is arbitrary. This is you assume. This has already been assumed, but these 3 currents, I3 and I2 and I5, they already been. Now again, you don't have to name this I1, because they already been given as a value. So it's just to have less confusion, you don't need to rename the currents with the values. Okay, so after we assign the nodal voltages V1 and V2 and assign the current, now we need to apply KCL at node 1. So we say apply KCL at node V1. Again, always we apply KCL at a non-reference node. Okay, this is a non-reference node, V1, V2. This is a reference node. It has a 0 voltage. So if we look to the node V1, we have current 5 is entering the node, and I3 and I2 are leaving the node, plus I2. Okay. Then we need to convert this current into voltages by using Ohm's law. So we need to know what is I2. Okay, so what's I2? So I2 is the voltage across the 4 ohm resistor divided by the 4. Now the voltage drop across the 4, it will be V1 minus V2 over 4. So then, and then same thing for I3. So I3 will be I3 going down. So we start with the V1 minus this voltage here, it's a 0 over the resistance 2. So then we have I2, again is V1 minus V2 over 4 plus I3, which is V1 minus 0 is V1 over 2 equal to 5. Now again, don't keep this fraction. We need to get rid of the 4 and the 2 by having a common number. What is the common denominator? It will be 4. So if we multiply both sides of the equation by 4, I will get rid of the 4 and get rid of the 2. So then my equation, it will be 20 equals, so 4 times 5 is 20, and then 4 times V1 minus V2 over 4, so the 4 cancel out, so it will be V1 minus V2, and then 4 times V1 over 2, it will be 2, 2 times V1 is 2, 4 divided by 2 is 2 V1, which is similar to this equation, so now we have V1, so it will be 3V1, so it will be 3V1 minus V2 equal to 20. Okay, which is the same as this equation. Okay. So again, after we reach that equation, we are done with the first mesh. Now we go, we're done with the first node. Now we do the same thing. We need to apply KCL at node of V2. Okay, so say apply, let's move this here, and we do apply KCL at node number 2. So this will give us V2 So coming to the V2 here, so we need to see what are currents entering the node. I see that I2 is entering the node, and the 10 also is entering the node, and then equal the current leaving the node is I1, which is 5, plus the current entering the node, leaving the node is I5. Okay, so current leaving the entering the node is I2 and 10. Current leaving the node is I1 and I5. Now we already have I2. Again, I'm going to write it down. So now I need to use Ohm's law to find I2 in terms of V1 and V2 and the resistance. So it will be V1 minus V2 over 4 equals to 5 plus I5. Again, I5 going from V2 to the ground or to the reference point. So that means I need to take V2 minus 0 over V2 minus 0 over 6. Okay, now I need to get rid of the 12 and the 4, so I multiply both sides by 12. Okay, to get rid of the 4, so I don't need any fraction in the equation because it would be very difficult to use a fraction or a decimal to solve the problem. So always try to find a common factor to get rid of the denominator and have it just digits or real numbers. So we need a real number rather than a fraction. So again, if we multiply this 12 times this term, so the 4 will cancel out and we have 3, so it will be 3V1 minus 3V2, and then 12 times 5 is 60, so that's 12 times 5, and then 12 divided by 6 is 2, so it will be 2V2. Okay, and then you collect the V2, so if you take V2 to the other side, you will have so V2, let me see here. So we have 3V1 minus 3V1, yes, 3V1 minus 3V2 equal to 60 plus 2V1. So if we move the V2 to the other side, it will be a negative. Negative, let me see here. I have too much here, let me write it down somewhere. So it will be 3V1, then minus, it will be minus 5. V2 is equal to 60. Okay, let me see. I think I forgot here one thing, that I have to multiply the 12 times 10 here. So I2 is equal to V1 minus V2 over 4. So I forgot to put the plus 10. So this is plus 10. So 12 plus 10 is 20. So let me put it down here. So this will be plus 120, okay, equal to 60 plus. So that one will be a minus here. So, okay, so now we have two equations in terms of the voltage, so we can use one of those techniques. Either we use the substitution method, or we use the Cramer's rule, or we use the elimination method. So again, these are my two equations. So let me see here. Maybe some of the method, it might be easier than the other. So let's put the two equations next to each other, under each other. So we have minus 3v1 plus 5v2 equals to 60. Okay, it seems that the elimination is the fastest way. So if we add the two equations, so 3v1 minus v1, this will be cancelled out. So it will be 5 minus 1 is 4, v1 equal to 80. So v1 will be 80 over 4, so it will be 20 volt. Okay, so this is 20 volt. Now I could use either equation, either this one or this one, to find the v1. So let me use that equation here. So 3v1 minus v2 is equal to 20. So I'm solving for v1. So 3v1 is equal to 20 plus v2. So v1 equal to 20 plus v2 over 3. So 20 plus 20 over 3. So it will be 40 over. So v1 will be 40 over 3, which is this. Okay, so again, the only thing you need just to pay attention is the how to write down the three or the node equations. Okay, again, you could use also the Cramer's rule as before, or you could use the substitution method. Let me give you a hint on the practice problem here. So again, we have node number 1, we have node number 2. So we need to assign currents here, top to bottom, left to right. Again, if you want, you can use bottom to top or right to left, that's up to you. So let's name this is I1, let's name this is I2, and this is I3. Okay, now we need to apply KCL at node 1. Okay. Again, apply KCL at node 1. Apply KCL at node 1. Again, node 1 is V1 and node 2 is V2. This is a reference node. So current entering the node, it's 1 amps plus, okay, anything entering the node? No. So it will be equals. Currents leaving the node, yes, I1 is leaving and I2 is leaving. Good, now apply Ohm's law. Second step, apply Ohm's law. Okay, to do that, so we have 1 plus I1, 1 equals I1 is going from the top, from V1 to the ground, which is 0, minus 0, divided by 2, and then I2 will go from V1 to V2, divided by 6. Okay. Okay, and then now we need to multiply both sides by 6. So it will be 6 equals to 3v1 plus v1 minus v2. So we have 4. So we have 6 equal to 4v1 minus v2. Okay, so this is the first equation. And then we go to the node number 2. So we need to apply KCL at node 2. So current entering the node, we have I2 and okay, current leaving the node is I3 plus 4. Okay, so 4 is leaving. That's the 4 amps. Okay, now apply Ohm's law. So I2, we have V1 minus V2. We already had it before here. Divide by 6. Now I3 is going from node 2, which is V2, to the ground, minus 0. Again, you don't have to write it down. Over 7 and plus 4. Okay, now we need to get rid of the 6, get rid of the 7, so multiply by 42. Both sides. Okay, so that's why I put 2 parentheses here. Okay, so this will be 7v1 minus 7v2. This will be equal to 6v2 plus 42 times 6 will be 816. And then you can collect the, bring this 6 to the other side, will be minus 13 v2. 13 v2 is equal to 168. Okay, now you could solve the two equations using one of those 3 techniques that we explained earlier. Now sometimes, okay, now remember that we, in the mesh analysis, when we analyze the circuit having the voltages, and then we analyze if we have a current. So sometimes the current, when we have a current source in the mesh analysis, is going to help us to find one of the solution, one of the variable. Now it's the same thing now. If we have a voltage source when we do the nodal analysis, is it going to be helpful or not? So there's 2 cases. One case when we have the voltage source, it's on the sides between a non-reference node and a reference node, okay? So in this case, V1 is equal to 10. So we get one of the solution. But if we have it in between V2 and V3, now V2 node and V3 node are a non-reference node. That will be a little bit difficult. So we're not going to cover this case. We will study case 1 when the voltage source is connected between the reference node and a non-reference node. Okay, so we simply set the voltage at the non-reference node equal to the voltage of the source, which means in this case V1, as I said, is equal to 10. So if the voltage is here, that will be good. If the voltage is here, that will be good. But if the voltage here or here, that's not going to be good. That will be a little bit difficult and takes more steps to do. So we're not going to go over this one. We just go over the case number 1 when the voltage is located between a reference node and the non-reference node, which is in this example here, which is will be very, very simple here to apply. Why? Now we have this point here, the node here. We have a node here, we have a node here. So we're supposed to have 3 equations or 3 node equations. Now, since this is a voltage source 15, so if we label this node here as V1 and this is V0 and this is V2, so immediately said, okay, V1 is equal to 15 and V2 is equal to 9. So now 2 of the 3 are already determined. And then we need to find now V0. Now how to find V0? We need to apply KCL at node 0 or node V0. Okay, so again, we don't need to apply KCL at node V1. We don't need to apply node KCL at node 0 because at node V2 because we already have the value and we already have the value of V1 and the value of V2 as indicated here. So now the only node we need to do is the node V0. So if we apply the node, again, after if these currents are not given, then we need to assume. Now, in this case, you assume I3 going going to going from V2 to V0. Okay, now let me see what we do for this one. So if we apply KCL, so apply, let's put it here, apply KCL at node V0. So we have I1 entering the node, I3 entering the node, I2 leaving the node. So apply Ohm's law. So I1 going from the 15 minus V0 over 5, and I3 going from 9 to V0 over 10K equal to I2 going from V0 to 0 volt over 20. And again, if we multiply this by 20, then we can have this equation. And then since it's only one unknown, it's easy to solve. And as again, when we have a voltage source using the nodal analysis between a reference node and a non-reference node, this will be very simple to solve. Again, this one here, so this node is given. So Vx, this is one node. This is the second node. So that one would be 24. So whatever that voltage is 24. So we have only one node to apply. So we have 3 milliamps coming in. If we assume a current going down, this going from left to right. So this is I1. This is I2, so 3 is equal I1 plus I2. Now I1 is going from Vx to the ground, which is 0. So Vx minus 0 over 5. This, remember, this is kilo ohms. So if you keep this as milliamps, that's fine. The K will cancel with the M or milliamps. The kilo ohms will cancel with the milliamps. So plus I2, again, I2 going from Vx all the way to the 24 volt, divide by 4. Again, we multiply by 20 times to get rid of the denominator and solve the for Vx, and you should get 20 volt. Okay, it seems that this is the end of the chapter, and I will see you, and thank you for watching. I will see you again in the next video.